Good afternoon, everybody. I want to welcome you to this inaugural celebration of Faculty Career Colloquium. So I want to give you a very brief background. This is a program that really got started from the strategic planning that was done with the faculty. And it really is designed and aimed at recognizing our senior faculty, especially past the stage where they become full professors. And it's meant to give a chance for every faculty who becomes a full professor every 7 years to have the opportunity to talk about what they're doing and have a chance to plan for the next 7 years. And so part of this is to present their work to their colleagues and then meet with the dean and their head to talk about what they plan to do for the next 7 years. So of course, one of the immediate questions that came up when we started planning this is what about faculty who are very senior and approaching retirement? And so the question was, there is no next 7 years, so what do we do about that? And do they need to be part of this? And of course, I felt these are the faculty who are the most experienced, the most accomplished, and with a lot of past successes that it would be critical for our current faculty, students, and staff to hear about. And so I'm delighted that the very first one of these is Jim Cooper, who is a faculty in electrical and computer engineering. And he is actually in that group who is, I think, officially retired. Almost, transitioning, sorry, okay. And I don't think Jim really needs an introduction, certainly not to this group. We will hear about a lot of his experiences, and I'm personally looking forward to it. So, Jim.
Claude, thanks very much. I want to thank everybody for, those of you who came from the main campus, for walking all the way out here. If someone knows how to dim the lights right over the screen, that would be appreciated. So Claude made it sound like this is an honor, and I'm glad to hear you say that because I'd looked at this and I thought it seemed more like a test than, and maybe a little bit of both. But I'm going to take the opportunity. So what I'd like to do this afternoon is to tell you, I'm going to go over a little bit of my highlights of my career, things that I learned some things from, and then talk to you about some of the issues that the university is facing. And so we'll go ahead and get into it. But my title is Real Engineers Get Their Hands Dirty, and we'll give some examples of that. First, I have to confess, I was a teenage computer programmer. And I'll tell you all about this. This was actually while I was an undergraduate, and I had a summer job during the summers of my freshman and sophomore years, which was 1864 and 1865. And we were doing computer programming. And I was working for an engineering firm, a civil engineering firm in my hometown. And they designed these rigid frame steel buildings. You've seen them all. The civil engineers had algorithms that they used to do the rigid frames that supported the buildings. And they were in the process of converting these algorithms into a computer, putting it into a computer so that it would take away the chances of computational errors and that sort of thing. They'd already done the algorithms for the main frames of the building. So I come in the summer and they wanted me to program in the algorithms for the built-up end walls. So the end walls are a little different because they don't support as much weight, but then they've got the end face and so on. I didn't do any of the real design. What I did was just take their algorithms and try to implement them into a computer program. Now I'll show you how old I am because this was the machine that we were using. The machine, so the company didn't have a machine. And there was no computer in our town. The nearest computer was 20, 25 miles away at the university. This is Mississippi. This is Mississippi State University. They have a good engineering program, certainly a good undergraduate program. The IBM 1620 was really state of the art. We had mag tape drives and we could type in things. but the console was the most impressive part. I mean, you got blinking lights. How many of you got blinking lights on your computers anymore? You got switches, buttons. I mean, you could start World War III with this thing. And the neat thing was, you know, you'd go into the room, you had this whole thing to yourself. So it's one person used it at a time. No timeshare, no network or anything. You walked in. We had 2 hours a week on the machine. So the company had leased the machine, and we could go in and we'd get in our 2-hour time slot. You'd go in the room, close the door. There's big windows. People could come by and look at what you were doing, and you could see and do your thing. So you ran the whole thing. Great experience. And the other thing I should show you is, so that's what it looks like, and our input was punch cards. And so everything was on punch cards. In fact, the output was punch cards. But anyway, what I learned from this was because we only got on the computer 2 hours a week, once a week, the other 4 days we sat and we did our coding. And we were using Fortran. This was Fortran 2, but it's basic Fortran. And we'd do the program, and then you had to debug the program. And you couldn't wait until the end of the week to try to run your program. So you'd sit there with a pencil and a calculator and a piece of paper, and you'd go through statement by statement, line by line, keep track of the value of every variable. You'd go through each do loop, and you know, hours and hours and hours. And you'd do different input variables to see that you'd caught all the possibilities. So what I really learned from this was attention to detail. And that's something every engineer learns at some point. So the devil's in the details. So I learned that at that point, but it came back many, many times later in my career. So anyway, I continued. I got my bachelor's degree. I got my master's degree. I came to Purdue, got a PhD, and I'm going to skip all the way through that. I graduated Purdue in 1973 and went to Bell Laboratories at Murray Hill, New Jersey, as a member of the technical staff. I was at Bell Labs for 10 years. It's a beautiful building. And for the first 5 years, I worked on integrated circuit design. The last 5 years, I was in the research area. So I'm going to talk a little bit about the first 5 years integrated circuit design. The first chip that we did in Cmos was a 256, that's not a mistake, 256 bit, not kilobit, not megabit, but bit. Cmos was really brand new. This was 73, 74. RCA had developed Cmos. Everybody else still was doing N Mos. So Intel and Motorola and TI, they were all doing N Mos integrated circuits. RCA had developed Cmos, and they had done small-scale parts, sort of T²L equivalent parts that you could buy in little packages and so on. We were trying to do regular integrated circuits, and the vision was that we needed the low power for the phone company. The phone company wanted to be able to put electronics in the telephone and not plug it into the wall. They wanted to power it with the electricity coming down the phone line, so it had to be really micro power stuff. So that was what we were working on. And here's the layout of the individual cell. What you see here is these are 2 p-channel transistors, p-channel Mosfets. Here are 4 n-channel Mosfets. And they're connected in a cross-couple latch. So this p-channel and this n-channel are gated by this polysilicon gate. Their drains are tied together, comes over and drives the gate of these 2 transistors. Their drains are tied together and comes over and drives that. So that's your basic cross-coupled inverter. That's your storage cell. And then to read it or write it, you have these transistors here, these 2 N channels that connect the cell output to the bit line. So you have a bit line and a bit bar line that run vertical, and horizontally is what's called the word line, and that turns on or off these transistors. So it's 6 transistors in the cell. Now the way we did the layout here, we had a big drawing table. We had a big sheet of Mylar, grid paper. It was gridded. We had a straight edge. We had 4 colored pencils and a pencil sharpener. And for each of these features, we would actually draw this in. So the metal layer here we always use red pencils for metal. We use green pencils for the polysilicon, blue for these implanted regions here, and black for these via holes. There's 4 levels. And you laid it out on paper, then you came in and you digitized, you got the coordinates, you established an origin someplace, you got the coordinates of each of these breakpoints and you coded it in, and each one of those went on one punch card. Now, we did the basic cell here, and then you went back and you stepped and repeated that. So this was not all done. You know, one cell was done, it was repeated, but then all the addressing and stuff had to be done, and all the wiring here had to all be done. And it was all on a bunch of cards, and we carried these cards around in a little tray, and you certainly didn't want to drop it and start all over again. But attention to detail again, that was important here. So anyway, after this initial chip, I went on to do a second chip, which I'll skip over. And the third one was one that was really important. It was going to be the first Cmos microprocessor. It's an 8-bit microprocessor. It was called the Mac-8 inside the Bell system. It was not sold commercially, but it was used within the Bell system. Actually went into production, and it was even as late as 1990, in the 1990s, they were still manufacturing, putting them into systems. So it was a very successful chip, as it turned out, but it was an 8-bit machine. It was sort of the equivalent of the Intel 8080 and the Motorola 6800, if you remember those. Those were both in-channel logic. This was the first CMOS microprocessor. So it was a pretty ambitious undertaking. The other thing that was interesting about this particular microprocessor, the other machines were, I think the right term is monadic addressing, I think. So with the Intel 8080, for example, if you wanted to add two numbers together, it would take 3 instructions. First instruction, go to location A, place the data in the accumulator. Second instruction, go to location B, add that data to the accumulator. And then third, take the accumulator, put it in location C. It took 3 statements. What they wanted to do with this machine is accomplish all that with one statement. So they had a statement that says, get location A, add it to location B, put it in location C. That was one statement. And so there was what we called an address arithmetic unit and a lot of registers associated with this more complicated addressing. And I think the instruction set was something like 40 or 45 instructions that it would execute. And it was specially optimized to run C code. So the Bell system had invented the C language. And we were going to program this in C, and they had a compiler that would compile it into machine code. And it's all designed in an integrated fashion. And this whole chip is going to comprise about 7,000 transistors, which was, for us, was a huge number at the time. In fact, the Intel 8080 was 6,000. So we were right alongside Intel in terms of complexity, but these were going to be CMOS and not NMOS. This whole chip was designed by 2 people. I was given the job of doing the control logic up here. This is basically this part. And Bob Krambeck, a colleague of mine, did the address arithmetic and the ALU, the arithmetic and logic units. That's basically the adding machine. And in order to do that, I wanted to learn how computers worked. So I went and got a book. It was, I don't remember the exact title, but it was the equivalent of Computers for Dummies. And I read it. And I decided I would design a machine of my own in my spare time and build it so I could learn how this thing worked. Real engineers get their hands dirty. And this is my machine. And it was built out of these little components here. These are all T²L integrated circuits, bipolar integrated circuits. In those days, if you were a hobbyist, you could buy these polyethylene bags of reject integrated circuits. There was an outfit called Polypacks. And you could order these, and they cost 25 cents a bag. And they were rejects. But these would be, you'd have a quad 2-input NAND gate in a package, and you'd test it, and you'd find 3 of the 4 gates fine. They work fine. So you just use those. And the one that didn't work, just don't use it. And so this was built that way. It had a lot of blinking lights, had a lot of switches. I love those things. And these chips over here, there are 12. These are memory chips. Each one of those is one of those 256-bit CMOS RAM chips that I'd worked on a few years earlier. So the Bell system was putting those out. So I put these guys in as memory. Didn't have much memory either. And I actually programmed this. Had a programming language, and I programmed it to play a game. I forget the name of the game now, but it was one where you would what was it called? Mastermind. Oh, you're right. Boy, my wife. It's a good thing she's here. See, what's happening as you get older, you just sort of forget these things. But it would play this game, and it was kind of fun. I mean, it'd give you a code, and you would guess it, and it would tell you, yes, your guess is right or wrong, and you would change your guess, and it was kind of fun. The guts of the thing, here's the backplane. I couldn't afford sockets, so I couldn't use wire wrap. Yeah, everything is soldered. You get to be really good at soldering, hitting these packages. But anyway, and built the compartment, the power supply, the 4 rectifiers, and the voltage regulator and transformer and all that stuff. I still got it. It still sort of runs. I mean, the lights blink, but it doesn't really run the program anymore. But anyway, you know, you've got to get in and do things. I really learned so much by trying to do this. The actual design of the microprocessor was atrocious. It was not at all the right way to do it, but it worked. And it worked. So anyway, getting back to the Mac 8, one of the challenges with a big CMOS circuit like that is you have rather complicated gates. So here's a very complicated logic gate. I won't even try to call it, give it a name in terms of the logic function. But there were a lot of these in the arithmetic logic unit and the address arithmetic unit. But in CMOS, for every N channel that it takes, you have a P channel transistor, and they're hooked in a complementary configuration. So for example, 1A and 1B are in series here. These are N channels. Their P channel transistors are in parallel. And this series branch is in parallel with this one. Up here, that parallel branch is in series with that one. So they're complementary. So whenever you have a logic state that gives you a conductive path from here to ground, and by the way, this is your output, that same logic state blocks conduction through here. So you don't get any direct leakage current. Very low power logic. The problem is it has twice as many transistors to perform the logic function, and we couldn't afford that. So we came up with something called Pseudo N Mos. And what we did was we took the N Mos pull-down array, fine, kept that, and in place of all of this, we put 1 P-channel transistor that was just turned on all the time. So it was a load. Now here, you do have leakage current when you have a path through here. And we got around that by clocking the array so that we only turned it on when on the one state in the cycle in an instruction we needed to compute something. So and we did several things. And then the other thing that came out of this, I don't know if any of you have heard of domino CMOS. That's a variant of Pseudo N Mos, but it's clocked. And that was another thing. So several patents and things came out of that. But we ended up building it. This part here is the address arithmetic unit. This is the control logic. So I did the part from about here up, and Bob Krambeck did the bottom part. We had 40 pins and so on. And let me just pick up a portion of this and I'll blow it up. This is called a programmable logic array. And each little, you can't really see the details, but each of these is a transistor. The locations of where you put the transistors in implements the logic function that you need for the control. So the machine has what we call a state diagram. Given an instruction, it will go through several states in sequence, you know, to execute the instruction. It comes back then, reads the next instruction, and that was all encoded in the logic here. So we had a state counter, which is 6 bits. So each state had a number, and depending on the instruction, you would go through certain states in a certain sequence. And so what was done here was the instruction register was off to the right, and the 8 bits of the instruction were brought in on these lines, so they gated some of these transistors. The state that you were in was brought around and brought in this way, and so each of these lines got a chance to look at the instruction and what the current state was, and then they would decide if they had a conductive path through here. If they did, then the control signals that were encoded here would be read out to end, and it would do 2 things. It would tell the machine what next state to go to, and it would then pull all the strings to make the processor do what it was supposed to do in that state. So that was what the way the thing worked. But this comes back to attention to detail, because each of these transistors are basically put in by hand, and every transistor was important. 7,000 transistors. You get one of them wrong, it doesn't work. Okay, they got to all work. So we got into debugging. So this was a very, very important project to the Bell system, and it had a lot of attention. In fact, the vice president was paying attention to this, because this was the biggest chip they'd ever tried to design. And the vice president was calling down every couple of days to see how things were going. So we went to mask, and we did the fabrication. It was all fast-tracked, and here we got our devices out, and we put them on the probe station, and we start supplying instructions to them. And it's not working. It's not working. 7,000 transistors. What do you do? Where do you start? So what we did, we went back. I'll go back to this. We got 6 very sharp probes on the probe station and carefully managed to put them down on 6 bits of the state counter. And these lines were not meant to be probed to, so it was very delicate to try to get in without shorting 2 lines and that sort of thing. But we got them down. We took those 6 bits and fed them to a logic analyzer, and we watched to see if it was doing anything. And it was doing something. And it went through a sequence of about 6 states and just repeated. And we looked at that sequence, and it looked familiar. It was the reset loop. It was running the reset loop. It's like somebody was holding the reset button down, and the machine was just going like that. Well, that was a big clue. So then we go back and look in the circuit, and I don't remember where it was here, in that circuit that processed the reset, and we found an error. We found a piece of metal, been laid out, wasn't supposed to be there, shorted the things like somebody holding the reset button down. So we take a probe, and we scratch the thing, we break it, boom, it springs to life, starts reading instructions, starts executing. Everybody was high fives, and you know, it was so neat. It wasn't perfect. We did have to go back and debug a few more things, but you know, basically, real engineers get their hands dirty. You go in and you find out why it doesn't work. So I learned some things there. Attention to detail as well. I skip over the part of 5 years I spent in the research area, but I came to Purdue in 1983 on the faculty, and I'll talk a little bit about that. I very soon got involved in silicon carbide. So I've been working in silicon carbide. It's a semiconductor material. I've been working at that for about 20 years now. So I'm going to spend just a few minutes talking about some of the things we did in silicon carbide. So first, let me explain what silicon carbide is. You're all familiar with silicon. All of our integrated circuits are made out of silicon. And silicon crystallizes in a very regular lattice. It's called the diamond lattice. All of the atoms are silicon, and they always sit in the same configuration. And the reason it's called the diamond lattice is because it's the same lattice that forms diamond. The only difference between crystal diamond and crystal silicon is that these are carbon atoms, those are silicon atoms. And both silicon and carbon come out of column 4 in the periodic table, meaning they have 4 valence electrons. And what they'll do in the bonding is this atom will share its 4 valence electrons with 4 nearest neighbors. And that's the same thing that happens with carbon. They're both semiconductors, actually. And one of the big differences here is the band gap energy. So the band gap energy, this is the energy required to break one of these electrons out of a bond and let it be free to move through the crystal so you can conduct current. So silicon has an energy, requires about 1.1 electron volts of energy to break a bond and create an electron. So at room temperature, there's enough thermal energy that you have a few holes in electrons. A hole would be a place where an electron had popped out of the bond. And both holes and electrons can move through the lattice. In diamond, it's a much higher band gap. It's about 5.5 electron volts. Silicon carbide is a material that is half silicon and half carbon. It looks like either silicon or diamond, but half the atoms are carbon and half are silicon. Each carbon bonds to 4 silicon nearest neighbors. Each silicon bonds to 4 carbons. You can't see the others because they're in the cell above. So it's a perfectly balanced semiconductor. It has a band gap energy of about 3.3. So you go 1.1, 3.3, 5.5. Now, diamond is very hard to process, and nobody has really made any kind of real devices in diamond yet. I'm going to take that out and just compare these two. The other parameter that's really important here is the breakdown electric field. So in silicon, the breakdown electric field is 0.3 megavolts per centimeter. This is the electric field that's enough to start tearing these bonds apart. When that happens, you get a huge number of carriers. You can't control the current flow. It just electrically, it breaks down. In silicon carbide, the breakdown field is about 5 times higher. Now, for power devices, that's very important, for power switching devices. And the reason it's important, and I won't go through the details, as we build a power switching device, there's a figure of merit that we always are concerned with, and that figure of merit scales as the cube of the breakdown field. So a factor of 5 turns into a factor of 125. So this, the same device in silicon carbide would have a figure of merit that was over 100 times better than silicon. That's the reason that there's been so much interest in silicon carbide as a semiconductor. We've been working on power devices for about 18 years now, and there are really several different types of power devices. We've worked on all 3 of these. I'm going to focus on the Mosfet, but let me just talk quickly about all of these. They are all very similar. You start with a single crystal wafer of silicon carbide. When we first started 18 years ago, we were using 1-inch wafers. We're now getting 4-inch and 6-inch wafers of single crystal material. You order it with an epitaxial layer, thick, lightly doped N-type layer. This is all single crystal, perfect crystalline, and you get this from the vendor. And then to do the fabrication, at the very top, we will implant a P-type dopant to form these P layers. We'll implant a heavier N-type dopant to form these layers. We'll grow a thermal oxide here. We'll open windows and put these metal contacts on it and alloy those to make electrical contacts. We'll put a polysilicon gate on top. And then by taking the gate positive, we can attract electrons to the top of that P layer and get an N-type path all the way from the source contact to the drain contact. And we'll have current flow. If we want to turn off the current flow, we'll take the gate to ground. This turns back into fully P-type, and you've got a blocking junction there. You don't get current. This is a switch, just on-off switch. This is an insulated gate bipolar transistor. If you look carefully, you'll see that this structure is exactly the same as this one, except all the doping polarities have been changed, just inverted. So N has become P, this P has become N, that N has become P. And what we have, this is again a Mosfet. This is a P-channel Mosfet, but it's in series with, now we have a diode here. And so when we turn this thing on, we get a forward bias diode. And there's a good reason for doing that, and it helps the performance. I won't go into that. The Thyristor is another important device. It looks just like the IGBT with one difference. Here the control electrode is a Mosfet. Over here the control device is a PNP bipolar transistor. So here the gate turns the device on and off through this insulator by an electric field effect. Over here the gate is actually attached to the N layer, and this is the base of the PNP transistor. As you go from left to right, the devices will carry progressively higher currents. As you go from right to left, they will run at higher frequencies. So it depends on your application, which one you'd want to use. I'll come back in a second and we'll focus on the Mosfet. Let me just say a couple of words about how these devices operate. What are they used for? The typical circuit is very simple, looks like this. We have a source of energy, a high voltage, let's say DC supply. We have some load. It could be a resistive load. It could be an inductive load like a motor that we're going to control. And this is a switch. We just want to turn this on and off. And we're concerned with the current voltage characteristics of that switch. So when the switch is turned off, we want to block. We don't want to have any current, and we want this to sustain a high voltage. And so the IV characteristics in the off state should look like that. Essentially no current. And as we go to high enough voltages, eventually the device will break down and we'll get uncontrolled current. So we need to stop short of this blocking voltage. That's one of our parameters. When we turn the device on, we want to have a large current and almost no voltage drop. We want it to be a dead short. Now, a semiconductor will never really be a dead short. It'll actually have some resistance. And if it has a resistance, the IV characteristic is linear. And the parameter we're interested in here is called the specific on resistance. So it's the resistance area product. As a device designer, what we want to do is minimize the resistance and minimize the area. We want to do both. And so that's the parameter that you might be interested in. However, if the device is a Mosfet, it does look linear. If I was comparing it to an IGBT or a Thyristor, they're not linear. they're more like diodes. They have an offset voltage. And I can't define a resistance here. The resistance is the slope of the line, and it's changing. So the better way to compare devices is to look at the power dissipation. If I look at the device here when it's in the on state, it gets hot. And there's a maximum temperature you can allow, and the package will only dissipate so many watts per square centimeter with that temperature drop. Typically about 300 watts per square centimeter for really good packages. So you have to operate the device so that it dissipates less than 300 watts per centimeter squared. Well, the power dissipation is just a product of the current times the voltage. So if I put a line here of constant power dissipation, it's going to be like a hyperbola. Now, I can operate up to this point. If I go any higher current, I dissipate too much power. So it turns out that we're going to look at the current that the device can carry at that specific power dissipation. Now, this parameter is good because it doesn't matter if the characteristics is nonlinear or if it's linear. I can quote that number and I can compare these two devices. So the metrics I'm interested in are the blocking voltage in the off state and this maximum current density in the on state. So I'm going to come back and just concentrate on the power MOSFET here. And that's where we've done most of our work. We introduced the first power DMOSFET in silicon carbide in 1996. And it looks like this. And this is just one cell of the device. This whole thing gets repeated. It's in parallel, left and right, and so on. So what we have in the device is we have a polysilicon gate electrode. It's completely surrounded with a silicon dioxide gate insulator. So this is glass, basically. We have a nickel metal source contact, alloy contact for the N-type source. We have nickel for the N-type drain. And the way the device operates is we have an electrical contact to the gate. It's back behind the screen. We take the gate to a positive voltage, and that attracts electrons right here to the top of these P base layers and converts them to N-type. And then we can get current flow through the device. So if I superimpose the circuit diagram onto this cross-section, it looks like that. The source is grounded. This region here and this one here and so on are all in parallel. This is where we control the current, and then the electron current flows this way. So electrons come in, flow downward, and go out through the load. And then to turn the device off, I take the gate voltage to 0. This goes back to P-type, current stopped. And the high voltage is held off by this PN junction. Now that's the reason, for those of you who understand devices, that's the reason why this region has to be lightly doped and very thick, so that the breakdown voltage of this PN diode is high enough. So that determines the parameters of this drift region. But let me show you some of the things. So we were the first to propose and demonstrate this type of a structure in silicon carbide. In 2004, we had another innovation where we introduced a cephaline short channel process. So here's what the wafer looks like when we get it from the vendor. The first step we have to do is implant the P base regions. So we need a mask for that. And earlier we'd used metal masks and then stripped it off and then gone back and done the next implant. In the new process, we use a polysilicon mask. So we grow up a thick polysilicon layer here and we pattern it. And this is going to be the implant mask. We then implant aluminum, which is our P-type dopant, and it's blocked. It doesn't go in where the polysilicon is. Now the next step is we want to put in our N+ regions, and we want them to be very closely spaced to the edge of the P region. We don't want to have a mask alignment tolerance. So the trick here is we now thermally oxidize that polysilicon mask. We just put it in and heat it, and it converts the silicon to the silicon dioxide. And when it does that, it expands by about, in this case, about half a micron. We then put photoresist on the outside edges to define the implant region, and we implant nitrogen, and that forms the N+ layer. And now the N+ is very precisely spaced, this edge from that edge, and we haven't used a mask. And we can easily get spacings of half micron or less. Now, you could go smaller, but in a power device with the high voltages, we have to withstand half micron, 0.3 of a micron. It's about as small as you can really go. So this really improved the performance when we came out with this process. Now, the next step, after we've stripped all of this stuff off the top, we grow a thermal oxide layer. This is going to be a gate oxide. we put down another polysilicon layer to form the gate, and that looks like that. So it's beginning to look like the real Mosfet. But now another thing that we added in 2004 was what we call a current spreading layer. And this is a region near the top of the N- layer that's more heavily doped. So by making it more heavily doped, we do a couple of things. One is when the device is turned on, we have current flow that comes vertically, and then it has to spread into this region. Well, you get current crowding here, and that raises the resistance. So by putting this current spreading layer in, it alleviates some of that current crowding, and it reduces the resistance. Now, the other thing it does, it allows us to make this spacing here very small, because otherwise, those of you who are familiar with devices will know that this is basically a JFET. It's a p-n junction FET that can pinch off the current flow through here. And so by making this layer more heavily doped, we can reduce that spacing. And the whole idea is to save area. So we got both benefits from that. Now, the next step is to put the source contacts in, and that used to require an alignment tolerance because you couldn't let the source contact get close to the gate. You couldn't let that short. Well, we eliminated that in 2007. So what we did in that process was we put a fairly thick polysilicon gate, and after we'd done all the other processing, we oxidized that. So it's now completely surrounded with an insulator. We do a light etch, just a very thin etch, short etch. This is a much thinner oxide, and we can remove that oxide without really taking off all of that. We now put a nickel metal right over everything, and it doesn't contact the gate because the gate's now insulated. And we've reduced the alignment, or eliminated the alignment tolerance here, and this is now maybe a half micron. So we've shrunk a lot of things. Finally, the last thing we did was we decided to remove these P+ contacts. And if you take them away, in 2007, we were getting cell pitches of about 8 microns or so with this full-up process. Now, you do have to make contact to the P base. It doesn't carry current, but you have to nail down the potential. So what we did was, as you go back along these fingers, we dropped in P+ contacts periodically. And then that was enough. So we have this region here. We've got a P+ contact. We have a different metal to make contact to it. And then the whole thing is covered with top metal. And this carries all of the high currents that the device has to carry. So it reduces some of that resistance as well. So we built the device. Well, I didn't build it. My students built it. But real engineers build things. And this is about 4 by 4 millimeters. Here's our bonding pad for the source. The source fingers run downward here. Another source bonding pad. They run upward. Here's the gates, and they run up and down, and they're interdigitated here. It's about 0.06 square centimeters. But if you take a small area and you blow it up, you can see a little bit better what's going on. Now, this granular-looking thing here, that's supposed to look like that. This is the nickel. When you anneal it and make a good ohmic contact, you get these grains, and it's perfectly normal. But these little gaps here, that's where we dropped in the P+ contact. So we don't have nickel, we've got aluminum here. And so the source contacts are fed vertically. The polysilicon gates run down in between. So this edge here is a transistor, and the edge here is a transistor, and this one is a transistor, and they're all in parallel. And the whole thing is covered with Thai gold top metal. So we built them, we cut them off, diced them in, and put them in packages, and we wire bonded, and that's sort of what they look like. And here's the IV characteristics. So we're actually carrying about almost 20 amps of current with a 4-volt forward drop in the on state. In the off state, we block over 1,200 volts. So it's a 1,000-volt blocking. And now the real figure of merit, you remember what I showed you earlier, is what is the current at a power dissipation of 300 watts. Here's your line, and that point is actually 158 amps per centimeter squared. This is a smaller device, but if you built 1 centimeter square devices, and people are almost there now in the production devices, this transistor would carry 158 amps. Now, this is some current. So this is pretty good, and we were really happy to see that. And all of that technology that I described to you, that most of it has come out of Purdue over the years, is now being used in manufacture. So Cree is selling these same silicon carbide power MOSFETs, and they have a couple of them, different ratings that they're selling. So a commercial product. So out of this, one of the things I can say is our experience has been that successful R&D is driven by new ideas. So there was a series of new ideas here, and we stayed with the same technology for many years and tried to milk it. And guess what? I've still got one new idea that I haven't tried yet, so I won't tell you what it is, but we're hoping we get a chance to try that. And real engineers get their hands dirty. Okay. So they asked me, Rago asked me to talk about what did I learn and what advice could I give. And so let me give you some thoughts. Funding. Well, Ollie, when you give your talk, I love this. I'm going to paraphrase your quote from one of your faculty members that you studied, was Uriv, I think maybe at Caltech. And he says, science is the most important thing, but funding is more important because without the funding, you can't do the science. You got to worry about the funding. I would say that the best way to attract funding is with new ideas. If you have a new idea, you can almost always go to an agency and get some kind of funding and get started with it. So new ideas are really, really important. Now, you may have seen the hype cycle, and I think it's relevant here. So it's a plot of, for any new technology, it's a plot of visibility of that technology versus time. Or you could say excitement. Or you could say funding versus time. And that cycle looks like that. Or at least sometimes it looks like that. So there's some technology trigger that occurs at some point. People get very excited. And the funding goes up and the visibility goes up. And you have these big national initiatives and so on. And sometimes there's going to be a peak. And you realize that the device really isn't going to change the world. And it's going to have more problems than you thought. It's going to be harder than you realized. And the excitement wanes. And there's some trough of disillusionment. And eventually you come up the slope of enlightenment. You say, well, no, but it's not going to solve all the world's problems, but it can do a lot of good things. And you get to this plateau of productivity. This is realism. Silicon carbide has gone through this whole cycle. So the technology trigger really came in the early 1990s. A lot of people jumped on the bandwagon at this point, and that's another thing I can tell you. It's critical to get involved at the very beginning. Trains leaving the station. It's only got so many seats on the train. Once the seats are filled, you can't get on. And you need to get on at the beginning. So we got on. We were very fortunate. I won't relate to you how that happened, but we sort of fell into it, but it was great. And we got on, and we rode it all the way up through the peak, which occurred, I would say, about 10 years later. So we had about 10 years of very strong funding. About halfway through this, we got a single grant that was worth over $10 million. And it funded us for 5 years. We had a huge group working on this. But there was a peak, and then there was this decrease in the early 2000s, and a lot of our competitors ended up sort of dropping out of the thing. And we kind of stayed with it. It looks like the trough was in the mid-2000s. There was still some funding, but it was pretty low. And now, in the early 2010s, we seem to be entering this slope of enlightenment, and we're kind of going up the slope, and we're pretty happy about it. And there's devices are going into production. Both Schottky diodes and now power MOSFETs, and there seems to be new programs coming on the horizon. The DOE has just announced a new major initiative, like $70 million on wide bandgap power devices, and ARPA-E has just put $27 million into it, and so it's coming back up here. But what's really happened is the technology actually went this way. All of this was hype. And so, but there was a steady development, and it is, so this is sort of the learning curve, and we're kind of getting up on the plateau now. So it's important to get funding at the start of the cycle. But it's also important to choose the right project. Because you might have a project that does this, but you're at the beginning, and you don't know where it's going to go. It might do this. Boom. A lot of them do that. How do you know the difference? I don't know the answer to that. But the key really is going to be to decide what not to work on. And some of it is luck, and some of it is intuition. And I've been doing it for 30 years, and I still don't know how to do it. I've been lucky with a few things and probably unlucky with a few things. The folks that are lucky, do really, really well. But the key, I think, to doing good research is to pick the right project. Teaching, I've taught for 30 years, and I've learned a few things. And my philosophy that I've developed over the years is make everything as simple as possible, but not more so. This is a quote was attributed to Einstein. Another way of saying the same thing, Steve Jobs said this: simple can be harder than complex. You have to get your thinking clean to make it simple. You might say, keep it simple, stupid. But so what I've found is that after you've taught a course a few times, you lose sight of how difficult that material is for the student to see it the first time. And it's really important to always approach the subject from the student's viewpoint, because you think it's all simple and you're presenting it, and you don't realize the student is struggling with it. The student has 4 or 5 other classes and maybe some other things on their mind besides that. And so, I don't know what that would be, but anyway, I always try to think about how can I make it really, really simple for the student. And I try to keep a lot of extraneous detail out and just keep things on showing simplest cases. So that's kind of the way I approach that. Facilities. I'm going to take that same phrase again about funding. Science is important, but facilities are important, because without the facilities, you can't do the science. And that takes me a little bit to the Birck Nanotechnology Center. So I was involved in this for about 10 years, and I want to tell you some of the stories, of the untold stories of some of the early days here. This is what our clean room looked like in 1996. This is our chemical hood. This is an evaporator, and then, so the students would wear the lab coats, but it wasn't really to keep the wafers clean, it was to keep them clean, because the equipment and this stuff was so dirty. He's got sneakers on. If you look closely there, you may notice the floor is broken up. If you walked around the labs and you looked a little more carefully, you'd see that that's what our clean room. This is our clean room. And so I had a student who joined me up from IBM for a master's program in '96, and I was taking him around and going to proudly show him the facilities, and I saw this, and I was really disappointed. I didn't realize it was quite that bad. So I went to see Dave Landgrebe, who was the interim head of ECE at the time, and I took him through, and he looked, and he was appalled. And he gave me permission to take Dean Schwartz through. And Dick had been involved in setting all these labs up in the '60s. At the time, Purdue was at the forefront of experimental electronics. We were one of the first universities to have an integrated circuit lab. But this was the '90s, and we were still in the same labs, and Dick was appalled. And so what he said to me is, put together a presentation that I can take to the higher administration. Let's see if we can do something to get these facilities upgraded. So here's a couple of slides from that regional 1996 presentation. And one of the things I pointed out was I plotted the square feet of clean room space for Purdue and our peer institutions in the Big Ten. And this is our national ranking. And you can kind of see where we were. Now, how did we even get to be number 8, with such a disadvantage that we were up against? And there were a few more slides in the thing, but basically, in that proposal, we said we need clean rooms. We need to have offices and some labs that are located close to that, and we need to have equipment. And if you think about the Birck Center now, we kind of have a little bit of all of those. But this was '96. And Dick took this to President Birring, and President Birring supported it. He tried to raise money. We didn't get any money raised, really. Martin Jiske came in as president in 2000, and within a year, he had raised $51 million. And in November of 2001, this announcement of launching of Discovery Park and a nanotechnology center. So Purdue has announced it will build a $100 million Discovery Park and has already raised $51 million for the first building, the Birck Center, which will be among the best of its kind in the nation. That was a promise. I think we kept that. So we had to do the design first. And we brought in, and George will remember this, we brought people from all over the university, the biologists and the chemists and the physicists and all of the engineers. And we got together to see how we could make an interdisciplinary building that would work. And that's what we came up with. So we had a little biology and chemistry, and a little physics, and a little biophysics, and a little physical, it was a little bit something for everybody. But we did try very, very hard, to make it interdisciplinary. And we had an architect firm that we hired. John Weaver was through us with all of this, and we had several conceptual drawings. This is the one that we actually selected. It does look like the existing building that we have now. These green areas are the labs outside the clean room. These areas are the service quarters. These were all going to be graduate student offices. It didn't turn out quite that way. These are faculty offices, and the big clean room sits in the back there. So we went through 2 years of design. That's, I think, why the building turned out as well as it did. We took so much time with the design. The drawings were made, and they pretty much ended up looking like we had envisioned. We broke ground in 2003. And the construction, we got the foundation. The ironwork went up. The walls and everything began to take shape. The interior work took a long time. This is one of the student offices that's being set up. This is the clean room. You can see the raised floor, perforated floor. The air flows through it. About 2 feet below is the waffle slab. John Weaver has taken his staff on hands and knees crawling tours underneath that and everything, so you can get up underneath there. The sub-fab beneath the clean room, all the equipment was eventually put in and hooked up. This supports the equipment in the clean room above. The clean room was finished, and it was certified eventually, and we had the big groundbreaking. Not the groundbreaking, but the dedication. And the principal donors were Mike and Kay Birck, and here's Neil Armstrong. Here's a presentation to the Bircks that President Jiske delivered. Here's a few of the crew. This is Don and Carol Cyphers. Ahmad Swade, who was the vice president of the design firm that implemented, and John, here looking dapper as usual. John was absolutely instrumental in helping us get it right. And all of you who are involved know how much he contributed. And George was there from the very beginning. And George and I went around and met with so many people and so on. We have the building. You look inside, it doesn't look anything like the clean rooms of 1996. You go inside, it's a huge area. It's one of the largest clean rooms and one of the cleanest clean rooms in the country at a university. Our lithography equipment is just great. We have a new oxidation diffusion tubes. This is an epigress reactor for silicon carbide crystal growth. We can do that at Purdue. Titan TEM, environmental high-resolution microscopes, cluster analysis, surface analysis tools, and so on. Now, my philosophy in this really was the facility is not the key to building the university at all. The faculty. You've got to start with the faculty, but without good facilities, you can't attract the faculty. And we tried for years to recruit outstanding young faculty to our university. And we competed with Illinois and Michigan, and they had these nice clean rooms, and we'd lose the battle. And people would go to these other schools. Once we had this facility, we started winning some of those same battles and pulling some of the best faculty away from our competitors, and it's helped a lot. Here's some of the people who have come to Purdue, either because of the Birck Center, or at least their research has been enhanced by the Birck Center, or their students have used the Birck Center. And they come from many different branches of engineering and from physics and chemistry and some biology and so on. It's had a big impact. This is just the faculty. And each one of them has many grad students. The building has 200 grad students with offices in the building. It's been running for 6 years. We've probably affected over 1,000 grad students already in terms of facilitating their research programs. Now, some final thoughts. So I'm going to get very philosophical here. Strategic planning is a big thing. And there's this Chinese saying that vision without action is a daydream. So having a plan is really good. If you don't implement it, it's kind of worthless, right? It's a daydream. So you need an action plan, a vision plan, and an action plan. The other part of the proverb says action without vision is a nightmare. Okay, so you need both. You really do need both. I want to talk a little bit about the nature of leadership, and this is going to be a very personal thing. I'm going to cite 3 or 4 examples of people I think were excellent leaders. One was Fred Terman. He was Dean of Engineering at Stanford after World War II. And as Dean, he spearheaded the creation of the Stanford Research Park as one of the first research parks at a university in the country. They took university land and they leased it to some of these firms like Varian and HP and GE and so on. And having that park really helped catalyze the emergence of Silicon Valley out on the West Coast. He was promoted to provost in 1955, and as provost, he aggressively expanded Stanford's science and engineering departments. And he recruited the leading Bell Lab scientists to the faculty. He brought William Shockley, Gerald Pearson, who invented the solar cell, the physicists like John Moll, mathematicians like John Linville, really the cream of the crop. That shifted the entire centroid of semiconductor development from the East Coast over to the West Coast. And that fueled the growth of Silicon Valley, but it also catapulted Stanford into the top ranks of research universities. What's remarkable about this is he had a growth plan. He didn't grow equally everywhere. He saw an opportunity, really, and he created a pinnacle of excellence about that one technology by getting the very best people. And because they were so good there, that helped attract other people in other fields. They wanted to be at a place like that. So I think that's the key, and he had the courage to do that. He had the courage to make the decision to go after these particular people. A little closer to the home, Dick Schwartz. Dick was Dean of Engineering, and as Dean, he initiated a strategic planning process to expand space. And the trustees were so impressed with this that they directed the next president to develop a strategic plan for the entire university. Now, we went to Dick in 1996. Dick had already had a strategic plan for engineering space. We came to him with this request to upgrade the lab space in solid state, and I'm not sure that was part of his plan. But when we approached him with this, he took our idea to President Birck. And the president asked him if this was engineering's top priority. And he said yes. He already had the strategic plan laid out. And he put this ahead of it. And without that support, the Birck building wouldn't have been built. He had the courage to say, this is the most important thing. Martin Jiske came to Purdue in 2000, and he vowed to move Purdue to the next level. He wanted us to go from excellence to preeminence. He created Discovery Park. He raised over $100 million to build the first 3 buildings. He hired 300 new faculty across the university, and he led this fundraising campaign that brought in $1.7 billion. He also had a strategic plan, but all of these initiatives came from him. The Strategic Planning Committee helped flesh them out, but he was the one who had the idea for Discovery Park. Steve Jobs, my 4th and last example. I'm just going to give you 3 quotes from Steve. It's really hard to design products by focus groups. A lot of times people don't know what they want until you tell them. So you don't go and ask other people necessarily. You have to know, as a leader, you have to have an intuition for what is really important, and you show people. He said innovation distinguishes between a leader and a follower. New ideas, I talked about new ideas, that's critical. And finally, he says quality is better than quantity. 1 home run is much better than 2 doubles. Now, Steve Jobs didn't try to hit doubles at Apple. He tried to hit home runs. He hit a few home runs, he struck out a few times. But if you don't try to hit home runs, if you don't really try to do that, you never hit a home run. What do all these people have in common? Their major initiatives didn't originate in committees. They had committees, they used committees, but the initiatives came from their leadership. Now, we're in a very exciting time where we're trying to grow the engineering faculty, and I think it's a huge opportunity But I want to go back to what Steve Jobs said, quality is better than quantity. Said another way, bigger is not the same as better. We want to be better. So if we want to improve the quality of the faculty, we have to hire people who are better than we are. We have to have the courage to do that. And it's tough, and you have to be very careful about what you do. But you need to look at people and say, are they on a trajectory to actually be better than us? I don't want to be around faculty who don't want, the really good people want to surround themselves with people that are better than they are. I felt all through my career I was surrounded by people that were better than me. Certainly at Bell Labs I felt that way. And as a student at Stanford I felt really that way. But it's a good feeling. That's what we want for Purdue. So we have to be careful with our hiring process. So to build a great university, some of the things that we talk about doing, we want to be diverse, we want to be multidisciplinary, we want to be global. These are really worthy things, but they're not going to lead to preeminence. Preeminence is only measured by the quality. So we want to do these things, but let's not lose sight. The critical thing is to get better and to get better as a faculty. We have an opportunity to do that. Let's take advantage of it. Now to close with my plans for the future. I'm on a partial retirement program. I've been on the program for about 18 months. It's been wonderful. I really recommend it to those of you senior people. Mark, listen to this. So I've had 18 months, and I used the opportunity to actually write a textbook, and it's coming out next year. It's called Fundamentals of Silicon Carbide Technology. I'm really excited about it, and I'm hoping to create some online courses that would be based on the textbook. So I'm going to continue to work on that. I want to do some other things besides the technical work as well. So one of the things I enjoy doing is getting up on top of these little hills out in New Mexico. This is Sophie, and my wife took the picture. So she's there with me. You just don't see her. This is part of a mountain chain. These successive peaks here run all the way up through Colorado. This is the southern end of the Rocky Mountain chain. If you look right over the edge here, and it's pretty steep, looking about 1,000 feet down, you see this beautiful little mountain lake. And where I was standing up there is right about there. And it's a lot of fun. This lake is only 12 miles from the center of Santa Fe. People think of New Mexico as a desert. It's not really. It's really a great place. So I'm looking forward to that. Thank you very much.
We can squeeze in a few questions.
Oh. Jim.
Yes, an interesting anecdote because I came and interviewed when they brought me through the Birck in 2004. And you had just finished building
the bridge
between Birck and Bentley. And
right.
I was very skeptical as part of the recruitment thing. So are they really going to allow biology? I was interested in bio-nanotechnology. They said, you guys are really serious. And so they led me in. It was still a hard hat area. Led me in through the Birck, led me down that overpass region, and then they stopped. And they kept me busy, and they stopped, and they started laughing. And the reason that they laughed was the bridge ended at Bentley at a wall. There was no door. And they asked me, now, who's shutting out who?
I took a picture of Jim standing at the end of that bridge, knocking on the wall. It's hilarious.
Yeah. No, but that's, I think that there's a great opportunity to try to merge the life sciences and engineering. I don't think we've done that yet. That's one of my, as the director, co-director of Birck with Dick for 5 years, and then I went back as interim for 18 months. It's one of my biggest disappointments so far, is we haven't successfully brought in the life science people. It's a huge opportunity. I think we still need to work on it, but that's the goal. Yeah, thanks, Jim.